A simple device can be built for just $3, and it can start generating electricity from the heat sitting on your rooftop right now. It doesn't require solar panels, wind turbines, or any complicated machines. Just two different metals and a temperature difference are enough to produce electricity. The concept may sound unbelievable, but it is based on a discovery made more than 2 centuries ago. In 1821, a physicist experimented with 2 pieces of metal and unknowingly uncovered a phenomenon that could convert heat directly into electrical energy. The discovery was simple, yet powerful. When 2 different metals are connected and one side becomes hotter than the other, an electric current begins to flow through the circuit. No batteries, no fuel, and no spinning parts are required. Only heat and a difference in temperature. The physicist who first observed this phenomenon formed a small loop using 2 metals, bismuth and copper. He placed one side of the loop on a warm surface while the other side remained exposed to cooler air. Nearby, a compass needle suddenly began to move. That movement revealed something extraordinary. Electricity was flowing through the metal loop even though no external power source existed. The scientist called the phenomenon thermomagnetism at the time, but the deeper explanation would only become clear years later. Scientists eventually named it the Seebeck effect, describing the direct generation of electricity from a temperature difference between 2 dissimilar metals. By the early 1900s, engineers had already begun experimenting with this principle in industrial environments. In 1902, factories with large furnaces noticed unusual electrical behavior in metal wires placed near extremely hot surfaces. One mining engineer working in Pennsylvania conducted a simple experiment using copper and iron wires. He pressed one junction of the wires against a furnace wall that was hotter than 400 degrees Celsius, while the other end remained exposed to cool outside air. The result was a steady, measurable electrical current. It was small, but it was constant and reliable. The engineer documented the findings and published them in 1903, sharing the discovery with the engineering community. For a brief moment, it looked as if the idea might develop into a new way of producing electricity. Yet after the initial publication, interest faded. There was no large commercial investment, no major development programs, and no widespread adoption in civilian life. During that same time period, the electrical grid was expanding rapidly across cities and industries. Power companies were building massive infrastructure and connecting homes to centralized electricity systems. Those systems depended on a specific model. Customers paying monthly bills, a decentralized technology capable of producing electricity independently, especially from something as common as heat, did not fit well within that model. Understanding the numbers behind this phenomenon reveals why it is so intriguing. During a hot summer day, the surface of a rooftop can easily reach 85 degrees Celsius, while the surrounding air temperature might remain around 32 degrees Celsius. That difference creates a temperature gap of about 53 degrees. Thermoelectric devices are capable of generating electricity with as little as a 5 degrees difference between hot and cold surfaces. A small thermoelectric module, roughly the size of a playing card, can produce around 1 watt of power continuously under favorable conditions. That amount may seem small, but over several hours it becomes enough energy to charge a phone or power small electronics. Stacking multiple modules together increases the output. 10 modules connected in series can generate approximately 10 watts of continuous electricity. That level of power can support LED lighting, small radios, or phone charging throughout the night. Unlike solar panels, these modules do not rely on direct sunlight. They operate on heat differences, meaning they can still generate power during cloudy weather, rain, or shaded conditions, as long as one side remains hotter than the other. With no moving parts and no mechanical wear, thermoelectric modules can function continuously without complex maintenance. Research conducted at a university in California estimated that certain roof surfaces could produce up to 4.3 watts per square foot during peak summer conditions when thermoelectric systems capture heat effectively. The most interesting part is that these devices operate silently and continuously without requiring sunlight to directly hit the modules. Even when solar panels experience reduced output due to cloud cover, heat stored in roofing materials can continue driving thermoelectric generation. In simple terms, the heat already sitting on rooftops could be turned into electricity if the proper devices were attached. The technology itself did not disappear completely. Instead, it continued to develop quietly in specialized fields. During the mid-20th century, thermoelectric generators found their way into military equipment and aerospace programs. Remote weather stations in extremely cold regions needed power sources that required no fuel deliveries and minimal maintenance. Thermoelectric systems proved ideal for those situations because they could generate electricity from heat sources without moving parts. Space exploration adopted the technology as well. In 1977, a deep space probe launched with thermoelectric generators built into its design. These generators converted heat from radioactive material into electrical power. Decades later, the same spacecraft continues transmitting signals from beyond the outer boundaries of our solar system. The reason it still functions is simple. Thermoelectric conversion can continue as long as heat exists and a temperature difference remains. Another fascinating discovery came from experiments conducted in 1834 by a French physicist who explored the reverse process. He found that when electricity passes through two dissimilar metals joined together, one junction becomes hot while the other becomes cold. This phenomenon became known as the Peltier effect. Together, the Seebeck and Peltier effects form the foundation of modern thermoelectric technology. The same device capable of generating electricity from heat can also create cooling when electricity flows through it in the opposite direction. Modern thermoelectric modules often use a compound called bismuth telluride, which is widely available and relatively inexpensive. A common module used in small projects can cost between $1.50 and $3. These modules are frequently labeled with model numbers such as TEC 2706 and are easily found through electronic suppliers. To make practical use of the electricity they generate, a small voltage boost converter is typically added. Boost converters can cost between $1 and $2 and allow low voltage output from the modules to be increased to usable levels such as 5 volts or 12 volts. Constructing a simple rooftop system involves attaching the hot side of a thermoelectric module to a heat-absorbing surface, such as a black-painted aluminum plate. A 12-inch aluminum square often costs under $5 at a hardware store. The plate absorbs heat from sunlight and roofing materials, transferring that heat into the module. The opposite side of the module remains exposed to cooler air, creating the temperature difference required for electricity generation. Under favorable conditions with a temperature difference of about 40 degrees, a single module can produce approximately 1.2 volts. Connecting multiple modules in series increases the voltage output. With 10 modules attached across the aluminum surface, the combined voltage may reach between 4 and 12 volts, depending on the temperature conditions. That electricity can then pass through a boost converter and slowly charge a 12-volt battery bank throughout the day. The same modules can also be used near a campfire to generate electricity. Instead of sunlight heating a metal plate, a hot stone placed beside the fire becomes the heat source. The thermoelectric module rests against the stone where temperatures range between 100 degrees C and 150 degrees C, while the opposite side faces open air and remains cooler. Adding a small aluminum heatsink costing around $2 helps keep the cold side cooler and improves efficiency. In this configuration, a single module can generate up to 2 volts at approximately 400 milliamps. Two modules connected in parallel and routed through a USB boost converter can produce enough power to charge small electronics directly from campfire heat. The setup operates silently and requires no additional fuel beyond the fire already burning for warmth or cooking. An outdoor camper demonstrated a similar arrangement during a wilderness trip in 2022. Using 3 thermoelectric modules and a simple boost converter costing $1, he managed to charge a GPS device, 2 phones, and a headlamp battery every night for an entire 7-day journey. The total cost of the hardware used in the experiment was just $11. What makes this phenomenon remarkable is that it is not a new invention or a recent breakthrough. It is a physical principle first observed in 1821, explored throughout the 19th century, and later used in advanced aerospace missions. The materials required are widely available, inexpensive, and based on well-understood physics. Heat differences exist everywhere, from rooftops warmed by sunlight to stones heated beside a campfire. Every sun-heated roof naturally creates a temperature difference between its hot surface and the surrounding air. Every fire produces the same contrast between hot and cool environments. Thermoelectric modules simply connect those differences and allow electricity to flow. The science behind it has been known for centuries, yet many people have never heard of it. The moment someone learns about this effect, the way they look at heat changes. Surfaces that once seemed ordinary, rooftops, metal plates, stones near a fire, suddenly appear as potential energy sources. The physics does not rely on complicated machinery or large power plants. It simply requires 2 metals and a difference in temperature. Once that idea becomes clear, it becomes impossible to ignore. Heat surrounds us constantly, and wherever a temperature gap exists, electricity can follow.